Alrighty. Welcome, physical science students. Good morning, good afternoon, good evening, and good night. Depending upon when you're listening to this, I hope one of those greetings satisfies the time you're doing it. Today we're going to cover two sections, 7.2 solute and solvent, and then 7.3, which I believe is rate of dissolving. We hit on this one a little bit Friday when we started talking about solutions. A solution is a homogeneous mixture where the solutes are small enough that they can't be filtered out and do not settle out. Remember, homogeneous means that it is mixed equally all throughout. Okay. So we also hit a little bit about the states of matter and what states of matter can be in a solution. We talked about how solutions can be liquids, for example, something as simple as sweet tea or salt water. They can be gases. Take a deep breath in, take a deep breath out. The air we breathe is a mixture of various molecules, or elemental molecules anyways, mainly nitrogen, some oxygen, carbon dioxide, etc. That is a solution. And then another solution can be solids. For example, alloys, mixtures between two different metals. So if you look at this statue here, this is a Japanese statue made of bronze. Bronze is a mixture or a solution of copper and tin, right? We call this, when we mix two different types of metals together into a solution, we call this an alloy. All right, so how do solutions form? They form when one substance is dissolved by another. The substance that dissolves is the solute. The substance that does the dissolving is the solvent. The solute is present in lesser amount than the solvent. This separates into individual particles which spread throughout the solvent. So keep in mind those solute particles are spread evenly throughout the solvent. In bronze, what are the solute and solvent? Give you a little hint here. In bronze, copper is the predominant metal and tin is the lesser metal. So using that information, you should determine that since copper is present in larger quantities, it will be the solvent, and then tin is the solute. The two metals are combined in a hot molten state, but they form a solid solution at room temperature. All right, what's your state? Oklahoma, of course. Just kidding. Matter in any state can be solute or solvent of a solution. For example, saltwater solution, salt is a solid, but it gets dissolved in liquid water. If you look at the table below, you see examples of multi-states of matter solutions. Gas dissolved in gas, can be dry air. You can also have a gas dissolved in liquid. This would be carbonated water, for example, carbon dioxide. If you enjoy carbonated beverages, such as a Coca-Cola or Dr. Pepper, that is actually what makes it fizzy, is dissolved CO2, carbon dioxide. Liquid dissolved in gas, this will be moist air. So if you ever kind of breathe on a mirror, breathe on a window, and you see it fog up, that is because you're breathing out a liquid dissolved in gas. Liquid dissolved in liquid would be vinegar. Solid dissolved in liquid, this will be something like sweet tea or salt water. You can also have gas dissolved in liquid and kind of be a foam sometimes. All right, many things that dissolve in water, that's why it's called the universal solvent. It's a good solvent because it's very polar. If you remember back when we were talking about covalent bonds, we talked about polar covalent bonds when essentially one atom has a stronger pull on the electrons. So the atom with the stronger pull will have a partial negative charge because it's got more of those negative electrons closer to it. Then the atom with the weaker pull will have a slightly positive charge because it's kind of doesn't have as many electrons close to it. When we look at water, water is a polar compound. The oxygen has what's called a stronger electronegativity. It's just another way of saying that it has a stronger pull on the electrons. So when they're sharing those electrons in that covalent bond between the oxygen and the hydrogen, the oxygen gets a little bit stronger, it's a little bit greedier, so it has the electrons a little bit closer to it. Since the electrons are negative, and the oxygen has more negative charge associated with it, so it will have a partial positive charge on it. We call this having a polar compound. When an compound has a partial positive charge on one thing, in an example of water, it'll be hydrogen because it doesn't have as many electrons near it, and a partial negative charge on another part of the molecule. In this case, with water, oxygen would have a partial negative charge. So again, a polar compound is just one that has a positively and negative charged end. Solutes that are charged are attracted to the oppositely charged end of water molecules. And this is what makes water really good at dissolving things and is able to pull the solute particles apart. Some substances don't dissolve in water. For example, oil and oil-based paints. It's nonpolar, so the particles aren't charged. As a result, the oil-based paint and oil in general doesn't dissolve in water. Now, there's this theory in chemistry that it's called like dissolves like. Polar or charged compounds will dissolve in polar or charged solvents. Nonpolar compounds or solvents will dissolve in nonpolar solvents and compounds. Polar solvents dissolve polar solutes. Nonpolar solvents dissolve nonpolar solutes. Watch a brief video.
Hello, my name is Kiana. Today we will cover solubility. We learned that sugar dissolves in water. This means sugar is soluble in water. The sugar particles are more attracted to the water particles than they are to each other. Some things are insoluble in water. Oil is insoluble in water. The oil particles clump together, get surrounded by water, and rise to the surface. They do not mix with the water. Another example is nail polish. Is it soluble in water? As we can see, it is not soluble. However, nail polish is soluble in acetone, nail polish remover. Another example is grass stains. The grass stains are insoluble in water, but soluble in rubbing alcohol.
Alright, so ionic and covalent solutes. So all solutes separate into individual particles when they dissolve. Particles are different for ionic and covalent compounds. So if you have an ionic compound, which is just remember a positive ion attracted to a negative ion. Again, these things form when oppositely charged metal and non-metal ions are held together in a crystal by ionic bonds. Just know ionic bonds is just positive and negative charges alternating in that crystal. Those ions are formed by the transfer of electrons. If you lose an electron, you become a positively charged ion called a cation. If you gain an electron, it's a negatively charged ion called an anion. Covalent compounds form when atoms of nonmetals form molecules that are held together by covalent bonds. Covalent bonds is the sharing of electrons. So there's really no charge differential. There's no what's called like electrostatic force, where you have a positive and a negative that kind of stick to each other like magnets. It's more along the lines of sharing these electrons, kind of like holding hands, more apt to it. Ionic solutes will separate into individual ions, whereas covalent solutes separate into individual molecules. For example, sodium chloride is an ionic compound. So when it dissolves into water, it will separate into a sodium ion, a sodium cation, and a negative chloride anion when dissolved in water. The negative oxygen ends of the water attract the positive sodium ions, because opposites attract, and the positive hydrogen ends attract the negative chloride ions. These forces of attraction pull the ions apart. So visually, if we want to look at it, it would look something like this, where on the left we have this sodium chloride crystal, and once we put it in water, we see those small water molecules. We've got the negatively charged oxygens, or the partially negative charged oxygens, and then the partial positive hydrogens. And so the partial positive hydrogens here, signified by the small red circles, will surround the negatively charged chloride, whereas the the negatively charged oxygens will surround the positively charged sodiums, and then the positively charged hydrogens will surround the negatively charged chloride ions. This is how it breaks the salt apart. Glucose is a sugar. It's a covalent compound. It forms glucose molecules C6H12O6 when dissolved in water. Sugar is polar like water, has positive and negative ends. And so essentially when it goes into water, the water and sugar molecules interact and it pulls the individual sugar molecules away from the sugar crystal. And then the sugar molecules are separated from the crystal and surrounded by water. So this visually it's going to look something like this, where we have the sugar molecules or glucose molecules here represented by the hexagons, and then we have the water molecules surrounding them, pulling them away from the sugar crystal. And this is how water dissolves sugar. In summary for 7.2, a solution forms when one substance dissolves in another. The substance that dissolves is called the solute. The substance that dissolves it is called the solvent. The solvent is usually present in a greater concentration than the solute. Solutes and solvents can be any state of matter, and then many solutes dissolve in water because water is a very polar compound. In general, in chemistry, like dissolves like. For example, polar solvents dissolve polar solutes, and nonpolar solvents dissolve nonpolar solutes. Ionic solutes separate into ions when they dissolve, and covalent solutes separate into individual molecules. Okay. All right, on your notes, you should have some explore more questions, so we'll watch this brief video and answer those questions accordingly.
Alright, so this video is going to be just an introduction to solutions. So what is a solution? Well, by now you probably know that a solution is simply a homogeneous mixture. So what is a homogeneous mixture? Well, let's review. A homogeneous mixture is a mixture of two or more different substances that has a uniform composition. So, in other words, if I have a solution, suppose I have a big beaker.
Nope, sorry about that.
Alright, so of solution. And I poured this solution into two smaller beakers. So we'll call this beaker A and then we'll call this beaker B. If I pour this one solution into two different beakers, then the contents of beaker A should have the same properties and same composition as the contents of beaker B. So that's what a solution basically is. Every part of the solution has the same composition. Now, a solution generally has two components, and those components are the solvent and the solute. The solvent of a solution, this is the majority component. And the solute of the solution, this is the minority component. So, in other words, the solvent is the substance that does the dissolving, and the solute is the substance that becomes dissolved. Now, if our solvent happens to be water, H2O, then we call this an aqueous solution. So, because water is so abundant and relatively cheap, water is used as what we like to call a universal solvent. Although the term universal solvent just means that water is abundant and that it behaves as a solvent in many reactions. If there was indeed a universal solvent, then it would dissolve everything. It would just eat through everything. There'd be no way to contain it. You wouldn't be able to have a container for it. So there really is no such thing as a literal universal solvent. But H2O is just a solvent in many reactions, and it is very abundant. So there's aqueous solutions. Now, we need to figure out how to express the amount of solute relative to the solvent. So that's called the concentration of the solution. So there's two general terms when we talk about solution concentration, and one of them is concentrated. So if a solution is concentrated, that means we have a lot of solute. So we have a lot of solute relative to the solvent. If our solution is concentrated. On the other hand, we have the term dilute. And if a solution is dilute, that means we have little solute. A little bit of solute relative to your solvent. So these two terms are relative to one another, but they're not absolute. And in chemistry, we like to have absolute things. So we need to find a way to quantify the concentration of a solution. And the most common way to quantify the concentration of a solution, there are many ways to do it, but the most common way is using molarity. So molarity is the amount of solute you have in moles divided by the total volume of your solution in liters. So notice that the molarity is not moles of solute over liters of solvent or moles of solute over moles of solvent. It's actually the moles of solute over the liters of the entire solution. So that means if I wanted to prepare a solution, so let's say I have a volumetric flask. If I can get a good pen. I'll just use a blue one. So this is my flask, and assume we have an aqueous solution. So that means our solvent is going to be water. So suppose I wanted to make a 1 molar solution of X. So I want the molarity to be 1 mole per liter. So I'm going to say a 1 molar, we use capital M for molar, 1 molar solution of just any compound or element, I'll just call it X. To get a 1 molar solution, what we need to do is we need to put 1 mole of our substance into the flask, and then assuming that this is a 1 liter flask, what we do is we dilute it with water. And then we add water to it and dilute it until we reach the mark on the bottle. The flask. So notice that we do not fill it up with H2O to 1 liter and then add the solution, and then add the substance. We add the substance first, and then we dilute the whole solution to 1 liter. So there you go. That's just a simple introduction to solutions, and in a couple of videos that follow, I'm going to go over calculations using molarity as well as solution stoichiometry.
Again, be sure to answer those 4 more questions for this section before moving on to the next.
All right, so this video.
All right, any questions? Feel free to email me tomorrow or today. I will be available as needed. Thank you very much. All right, 7.3, rate of dissolving. So if any of you heathens like sweet tea, obviously you know you have to dissolve the sugar in the tea. I don't know why you would do that. It makes it taste so terrible. But we talked a little bit in class about things you can do to increase the rate of dissolution. So some of the factors include various ones. For the purpose of discussion, we'll use the example of the dissolving sugar entity for kind of our example. So what could you do to dissolve the sugar faster? Well, you can do several things, include stirring, adding energy in the form of kinetic energy by stirring, increasing the temperature, which is just increasing the temperature or increasing the movement of the molecules or the particles. Remember, temperature is just a thermometer for atoms, or a speedometer for atoms. It's just a measure of how fast molecules and atoms are moving. There's also the size of the solute particles. We talked about how granulated sugar will dissolve faster than a cube of sugar. So stirring speeds up the rate of reaction, distributes the particles throughout the solvent, basically gives increased contact area. Temperature. Generally, solutes dissolve faster in warmer solvent because particles have more energy of movement. This is kind of a visual representation of sugar dissolving in water. Cold water, it takes longer. Hot water, it does faster. Particle size. For a given amount of solute, smaller particles have greater surface area. This means there's more contact between particles of solute and solvent, expressed visually here. So essentially for dissolution to occur, the red circles have to come in contact with the green circles. On the visual of the left, the red circles can just attach or come into contact with the green circles on the outside of the shape. But if you increase the surface area by making smaller particles, the red circles can interact and attract or attach to the green circles in a higher number of options. So in summary, the rate of dissolving of a solute in a solvent is faster when the solute and solvent are stirred. The solvent is warmer, or the solute consists of smaller particles with more surface area. Any questions? Cool. For those of you that stayed to the end of the video, this is an opportunity for extra credit. So for your virtual day, find your favorite science meme. You can find a new one if you don't already have one. I don't expect you to already have one. Send it to me by 3/25 for extra credit. Now here's the deal. There's 100 points of extra credit available per subject. So the less people you tell about this, the higher and more points you'll get. For example, if only one person within physical science emails me, that one person will get 100 points of extra credit. If 2 people, then it will be 50 points per person. If 4 people, it will be 25 points per person. So this incentivizes you to keep it to yourself. If you listen to the entire presentations, good job for you. Now that you do that, you have the opportunity for extra credit. Thank you very much.